All right, so let's go ahead and get started. We got our last experimental technique that we're going to be introducing today, nuclear magnetic resonance spectroscopy, or what they call NMR. All right. We have introduced these three experimental techniques, IR, mass spec, and now NMR, and we do so kind of early in the course because they tend to be fairly difficult. First of all, they show up in lecture and in lab. NMR in particular is a little complicated, and so we want to get lots and lots of practice throughout the course of this semester. All right, so that's going to be our goal here, is to have introduced these techniques, but we're going to be doing NMR, IR, mass spec throughout the rest of the course, right? So we get really good at it by the time we get to our final exam, okay? So NMR, let's kind of lay out a little bit of background here. So NMR is another spectroscopy. So we got that same basic setup that we talked about for our IR spectroscopy as well. You have some photon source that you're sending into your sample, right? Sending in photons to our sample. Those photons will interact with the molecule in your sample by being absorbed. So some of them will come back out the other side and others will be missing, right? And then we have a detector to see what we actually get back out from our sample. So the difference is what photon source we use, where on that electromagnetic spectrum we are. All right, we talked about last semester you did UV vis spectroscopy, so using photons in the UV invisible range. We talked about IR, using longer wavelength photons in that infrared portion of our spectrum. All right, and now NMR uses these very longest photons here, our radio wave portion of our electromagnetic spectrum. All right, so NMR. All right, again, another form of spectroscopy, but we're going to use photons from the radio wave. Portion of our electromagnetic spectrum. All right, and so these photons are going to be interacting with our sample. When we were talking about UV vis, they were interacting with electrons, all right? When we were talking about IR earlier last week, what was that interacting with in our molecules? The bonds, right? So remember, those bonds are vibrating back and forth. When they absorb a photon in the IR portion of our spectrum, they start vibrating even more frequently, right? So IR was interacting with our molecules' bonds. So what about NMR? All right, these photons, they're going to excite the spin of an atom's nucleus. All right, now this is one of the first complications of NMR spectroscopy. Instead of like vibrating bonds, making bonds go a little bit more, vibrate a little bit faster, all of a sudden it's interacting with the spin of these particles. And we don't really have the nice, neat mental picture for the spin of a nuclei that we do for bonds vibrating, all right? So that's one of the things that makes NMR a little harder to wrap your head around. This concept of spin was first introduced to you back talking about electrons, right? Electrons, you can fit two of them into an orbital as long as they have opposing spins. It turns out that this concept of spin extends to all of our particles that we have out there. All right, so now we're talking about the particles that live in our nucleus, our protons and our neutrons. They also have a spin associated with them. And that spin is what's interacting with our photons in our NMR spectroscopy. All right. Cool. And I know everybody's like, yeah, no, totally. I knew that. Like, that was exactly what I expected to be happening. No, it's a really weird. Again, spin being a quantum mechanics-based concept is a little bizarre. What you'll find is people who specialize in NMR pretty much only do NMR because it's a really complicated math field that's buried in quantum mechanics. And trust me, they go all sorts of deep into that. We're going to be scratching the surface, but it is itself a very complicated theory, in part because we're talking about quantum mechanics here. All right. In order for this to occur, though, in order for photons to interact with the spin of a nucleus, it requires a strong magnetic field. Okay, so why is that? I'm going to try to paint a little bit of a picture for you as to what's going on at the molecular level if we shrink on down into our magic school bus, all right? But again, it is kind of bizarre, so you're just going to bear with me, okay? If we have a sample of our molecules, our atoms, they have these spins associated with those nuclei, the protons and the neutrons, all right? But those spins are kind of oriented in all different directions. Right? There's not any sort of rhyme or reason as to the direction of those spins until we apply a magnetic field. And then all of a sudden, all those atoms have to align their spins with that magnetic field. So everything's kind of pointed in random directions until we apply a magnetic field, and then everything flips so that they're either aligned with the magnetic field, pointed in the same direction, or aligned against the magnetic field. Right? So in the absence of a magnetic field, everything's pointed in random directions. As soon as we apply that magnetic field, we get a big magnet. Everything's going to align itself either with or against that magnetic field. All right? So everybody's got to pick real quick whether they're going to be with or against that magnetic field. Now, when we send in a photon, that photon gets absorbed by exciting the spin state of that nuclei. It will take one of these. It turns out that there's a little bit of an energy difference between the nuclei that are aligned with the magnetic field compared to those that are aligned against the magnetic field. It's a little bit more energy to be aligned against the magnetic field. So when we send in a photon, our photons get absorbed by exciting a nuclei from the spin state where it's aligned with the magnetic field to where it's aligned against the magnetic field, right? So these photons are flipping the spin of these nuclei within those magnetic fields. That's why those photons are getting absorbed, okay? So we're just going to note these photons, they flip the spin of that nuclei. Whoops. In that magnetic field. That's why they're being absorbed. We're just going to say why they're absorbed. Okay, so, and yes, I know, a little bizarre, all right? You're just bearing with me here. These particles in our nuclei are protons and our neutrons. They have spin. If we throw a molecule in a magnetic field, those spins will align for or against that magnetic field. And then these radio wave photons that we're sending in, the reason that they get absorbed by those molecules is because they flip the spin of those nuclei. Importantly, not all nuclei are NMR active. So you can't see every atom in an NMR. There has to be an odd number of protons and neutrons in there, an odd mass number for those atoms to actually interact with that magnetic field. So the two that we are going to pay the most attention to, so these are all active nuclei in an NMR because they all have an odd mass number. All right, the two that we're going to focus on in organic chemistry is hydrogen, H1 NMR. So most abundant hydrogen isotope just has one proton and no neutrons. So H1. And then the other one that we're going to look at is carbon-13 NMR. This is the rare isotope of carbon, which has that odd mass number. So most carbons have 6 protons and 6 neutrons. There's a small amount of carbon out there that has 6 protons and 7 neutrons, or that odd mass number. So both of these would interact with that magnetic field, with our NMR. All right, and then just some terminology here. We're going to look at our NMR spectrum. All right, what we have on our x-axis is what they call chemical shift, but it's really just the frequency of those photons that we're sending in. Right, so just like when we were talking about IR, every point along our x-axis here represents a different photon that we're sending into our sample. If those photons get absorbed, you see peaks in that region of your NMR spectrum. All right, and then just kind of some terminology that we're going to throw around. The higher chemical shifts over here on the left-hand side, we call this the down field of our NMR spectrum. So if I say a peak is down field, that means over on the left side of our graph. And if I say a peak is up field, that means it's over on the right side of our graph. Cool. All right, so we're actually going to start with carbon-13 NMR because it's a little bit simpler of the two. All right, so carbon-13 NMR analysis. If I look at a carbon-13 NMR, there's 3 important pieces of information that we can get from that graph. The first is the number of peaks that we see. All right, the number of peaks on our carbon-13 NMR graph correspond to the number of chemically distinct carbon atoms. All right, and this is our first skill that's going to take a little bit of work to get good at, is looking at a molecule and being able to see how many chemically distinct carbon atoms it has. So first of all, what do I mean by chemically distinct? All right, I'm going to leave some room here. We're going to talk about other ways that we analyze our carbon-13 spectrum, but let's just kind of start picking this apart here. What do we mean by chemically distinct atoms? All right, an atom is chemically distinct if it is in a unique chemical, aka bonding environment, all right, and what we're going to see is that it's closely related to a molecule's symmetry. Okay, so let's look at an example here. We're going to go a simple 5-carbon alkane pentane. How many carbons do I have in this molecule? 5, right? So we have 5 carbons. All right, but we have only 3 chemically distinct groups. All right, so let's just label these carbons 1, 2, 3, 4, 5. All right, so certain of these carbons are grouped together, meaning that their chemical environment is the exact same. Okay, so these two on the end, carbon 1 and carbon 5, they are in the exact same chemical environment. All right, if I were to shrink down into my magic school bus and stand over here on this carbon, I look out and I see a 4-carbon chain after that, right? That's the exact same as if I was over here on this carbon looking in the other direction, right? So those chemical environments are identical for those two carbons, okay? What's another chemically distinct environment? 2 and 4, exactly, right? So if we stand here on this carbon and we look to the left, we see 1 carbon, right? 1 carbon over there, 3 carbons over there. Well, that's identical to if we were to jump over to carbon 4. Again, we look over here, 1 carbon, over there, 3 carbons, right? So those are identical chemical environments. And carbon 3 is sitting all by itself. All right, so these are my 3 distinct chemical environments that I have in this molecule. So if we were to look at the carbon-13 NMR spectrum of pentane, of this molecule here, we would expect to see 3 peaks, 1 corresponding to each of these chemically distinct environments. Okay, and again, it's related to the symmetry of this molecule. What you want to note is that if we cut this molecule in half here, it's got this plane of symmetry right down the middle. Meaning that the left-hand side and the right-hand side are mirror images of one another. All right, and since these orange ones are mirror images of one another, they're in the same chemically distinct group. These red ones are mirror images, they're in the same chemically distinct group. The one on that plane is all by itself. All right, so here are my 3 chemically distinct groups of carbons. I have carbons 1 and 5, I have carbons 2 and 4, and then carbon 3 is all by itself. All right. So let's practice, and this is going to take a little bit of skill here, all right? But let's practice trying to find how many peaks or how many chemically distinct environments there are for a given molecule. All right, so everybody take a second. You're going to tell me, I guess to be clear, we're looking for the number of peaks in our carbon-13 NMR spectrum. That's what we're going for, which again is how many chemically distinct groups of carbons there are in that molecule. don't know. Let's see. All right, let's do this first one. I got 2 carbons, all right, but are they chemically distinct? Am I going to get 2 peaks? No. These are in the exact same chemical environment. We can see this plane of symmetry right down the middle of our molecule. So these carbons here are mirror images of one another. I'm just going to see 1 peak in my NMR spectrum for this molecule, for ethane. All right, what about these 3 carbons here? How many peaks would I expect to see? 2, right? So now I have this plane of symmetry right down the middle, which means that these 2 are going to be found in the same group, but this one's all by itself here. All right, again, these 2 are mirror images of one another about that plane. All right, what about this one? Do we have any planes of symmetry here? I twisted it on its side, but we still have this mirror. I can fold this molecule in half, right? Right down that carbon there. All right, if I fold my molecule in half down that line, I match these 2 are in the same group. These 2 are in the same group. And all those carbons sitting on that line are going to be in their own group. So for this one here, I would actually expect to see a total of 5, 1, 2, 3, 4, 5 peaks. Okay, and that's kind of the amazingly powerful part of NMR is it's so sensitive to the exact chemical environment that even though these are both CH2s, they're in a slightly different chemical environment, so they're going to absorb at a slightly different portion on my NMR spectrum, right? I'm going to get 1 peak corresponding to this group and 1 peak corresponding to this group. I'm going to get 5 peaks total, right? But these are pretty similar looking, but they're slightly different because of that methyl group. And then this one's tricky. What about this one? Does anybody have a guess? 1. All right, there's only going to be 1 group here. If I'm standing on either one of these carbons, everything looks the same, right? There's just 5 carbons in a ring going around. Same thing if I'm standing over here. It's going to look the exact same. This one has a ton of planes of symmetry going down here, here, here. Kind of maybe the easier way to think about it would be that it has rotational symmetry. So if I pick this thing up and rotate it, well, it won't look the same because my drawing sucks, but if my hexagon was perfect, you would see that it would look the exact same. All right, so this has this 6-fold rotational symmetry, so I only get 1 peak here. All 6 of these carbons are going to sit in the same chemical environment. All right, so this is our first skill that we're going to need to have. It's going to take a little bit of work. We're going to have to practice it a little bit, but looking at a molecule, we want to be able to determine how many chemically distinct environments it has, because again, that corresponds to the number of peaks I would see in my NMR spectrum. Okay, so that's our first piece of information that we get from our carbon-13 NMR. Number of peaks tells us how many chemically distinct groups we have. Our next piece of information is the chemical shift of those peaks. Remember, that's what we label our x-axis as, is chemical shift. So by chemical shift, I mean where on that x-axis we find our peaks. And that tells you about the chemical environment of that particular carbon. All right, so similar to IR, right? Depending on where that peak was on the x-axis, it told us some information about that peak. Same thing with NMR, all right? Specifically looking at carbons now, right? We're talking about carbon-13 NMR. It turns out that our regular old carbons with their single bonds are down here. Would this be upfield or downfield? It's kind of backwards from what I feel like it should be. All right, remember we called that the upfield portion of our spectrum. All the way to the left is downfield. All right, so our sp3 hybridized carbons absorb upfield. If we have a carbon-carbon triple bond or a carbon bound to a heteroatom, all right, it says carbon, nitrogen, carbon, oxygen, really carbon and any heteroatom. It's going to be a little bit further downfield. If we have sp2 hybridized carbons, that's even further downfield. And the one that absorbs way, way downfield are these carbonyl carbons. Okay, so our carbons will absorb at a different portion of our spectrum here, depending on their exact chemical environment. So we can compare two molecules here, all right? This one here we said only has one peak, and that's an sp3 hybridized carbon with some hydrogens, so that's way upfield. Benzene has that same six-fold symmetry that we were looking at before, so we're only going to see one peak. But now that absorbs way downfield because it's in those those sp2 hybridized carbons. So where exactly you absorb on your x-axis tells you a little something about the chemical environment of those carbons. All right, and then the last thing that we're going to look at when we do our NMR analysis is what we call the integration. All right, so we don't do this manually. The computer does it for us, but it would go in and integrate this peak. What do I mean by integration? What am I calculating? The area under the curve, right? We remember this from calculus. Anyways, the computer goes in and tells us what the area under this curve is, and that corresponds to the number of carbons in that peak. All right, so my integration, my area under my curve, under my peak, this gives us information about the number of carbons in that chemically distinct group. All right, so what we're going to do is we're going to look at a few molecules and we're going to try to predict what our carbon-13 spectrum would look like here. All right, let's do this one first. First, we need to figure out the number of peaks. So we're going to do this one together, and then I'm going to have you do two of them on your own. All right, so let's look at this molecule here. We need to figure out how many peaks we're going to expect to see in our carbon-13 spectrum here. What do we think? How many peaks? 2, right? So I have this plane symmetry down the middle here. These two are going to be in one group, and this one's going to sit all by itself. Okay? What about my integration of those peaks? I know I'm going to see 2 peaks. All right? If I calculate the area under the curve, for my orange peak, what would I expect my area to be? Since this area corresponds to the number of carbons that are in that group. How many carbons are in the orange group? 2. So I would expect an integration value of 2. And what about my red peak? What would my integration value be? How many carbons are in that red group? 1. Cool. So I should expect 2 peaks. One of them will be twice as big as the other one. And so if we look at our spectrum here, this is what we see. All right, and we can tell by our integration values here that this corresponds to that red group, that orange group of carbons, right, with my integration value of 2. And this smaller peak corresponds to my red group of carbons, integration value of 1. All right. We also just want to note that since this red carbon is bound to this heteroatom, that's why we have this peak further downfield, right? Our CH3s are going to be upfield. If it's bound to a heteroatom, that's further downfield. Cool. All right, so we're going to do these bottom 2 here. For each one of these, I want you to tell me how many peaks you're going to see and what the integration value of those peaks should be. All right, let's do this one first. How many peaks would we expect to see? 3. So again, right down the middle, we have that plane of symmetry. These 2 are in the same group. These 2 are in the same group. And then this one's all by itself. All right, what would be the integration of that orange group? 2. What about that red group? 2, and then that green group? Just 1. All right, and which peak would we expect to see furthest downfield? What color? Our green one, bound to that heteroatom, right? So let's see. Here's our spectrum here. Integration of 2, integration of 2, and yes, we can tell this one all the way downfield here with our integration of 1 corresponds to that green peak. Cool. All right, so what about this one here? How many peaks would we expect to see? So this one actually has 4, okay? And again, this is how sensitive NMR is if we look, this is a CH3 over here, and this is a CH3 over here. but they are not equivalent. One of them, its next door neighbor has a chlorine on it. The other one, its next door neighbor does not. All right, so this is how sensitive NMR is that it's going to be able to distinguish between these two methyl groups here, these two CH3s, because of their exact chemical environment. All right, so in this case, all four of these, there's no symmetry in this molecule. All four of these carbons live in that same live in distinct chemical groups. So for this one here, we would expect to see a total of 4 peaks, each with that integration value of just 1. All right, so that's how sensitive NMR is it can distinguish between the exact chemical environment. Blue and orange are both CH3s, but they are not in identical chemical environments, so they're not going to absorb in the exact same place on our spectrum. Cool. And then this is the only one that we can really assign easily. Kind of when we get more advanced, we might be able to assign these ones here. But this one we know all the way downfield must correspond to that carbon with my chlorine bound to it. Cool. All right, so carbon-13 NMR, we get information from the number of peaks we see, tells us how many chemically distinct carbons there are in our molecule. Where on the x-axis it absorbs tells us about our chemical environment. And then the integration, the area under those curves, tells us how many chemically distinct, how many carbons rather are in that chemically distinct group. All right, so now we're going to graduate to H1 NMR. And what we're going to see for our H1 NMR is very similar. All right, in fact, all that information that we got from our carbon-13 NMR, we get from our H1 NMR. All right, so the number of peaks also tells us about the number of chemically distinct groups. But now we're not talking about carbons, we're talking about hydrogens. Okay, so then where on our x-axis, our chemical shift is another piece of information that we get. Again, telling us about the chemical environment of those hydrogens. All right, and similar to our carbon-13 NMR, we have a little bit of a cheat sheet here for the environment of the hydrogen and where we can expect to see the chemical shift of that hydrogen. This is not something you have to have memorized. This is a tool that you're going to be able to use, all right? But we can see that, for example, a methyl hydrogen absorbs way upfield, whereas if it's attached to an aldehyde, for example, it's way downfield, right? So the exact environment of that hydrogen tells you where on that x-axis you're going to see a peak, similar to carbon-13 NMR. Okay, we also have our integration. So the area under that curve tells you the number of now hydrogens in that chemical environment. Say in that chemical group. All right, so all the same pieces of information that we had from carbon-13 NMR, we get from hydrogen NMR as well. All right, but now there's one extra piece of information that we get from H1 NMR that we don't get from carbon-13 NMR, what we call the multiplicity of those peaks. All right, the multiplicity of a peak in H1 NMR tells you about the number of neighboring hydrogens. To that chemically distinct group. All right, so what exactly do I mean by multiplicity? Well, if we looked at our carbon-13 NMR, we always had these nice, neat peaks. All right, maybe they were a little bit larger than their neighbor, but they always just went straight up and down. For hydrogen NMR, you see this sort of splitting pattern in our peaks. And this is what we call the multiplicity of those peaks. So instead of just seeing one spike, you may see one, or you might see two right next to each other. Or you might see what we call a triplet, so it splits up into three. Each one of these would be considered one peak. It's just got this splitting pattern associated with it, which we call the multiplicity of that peak. Okay, so our multiplicity here if we have a singlet, that means the multiplicity is 1. We just have one peak. If we have a doublet, we see these two peaks, 1, 2. All right, so our multiplicity would be 2. A triplet, what's our multiplicity? 3, right? We see these 3 peaks. Quartet, we see these 4 peaks, et cetera, et cetera. All right. So with H1 NMR, our peaks show this splitting pattern. And depending on our splitting pattern, that gives us information about the number of neighboring hydrogens to this particular group here, right? This peak corresponds to a chemically distinct group of hydrogens. How many neighbors it has tells us about our splitting pattern. And we got this simple relationship between the two. Our number of hydrogen neighbors is equal to our multiplicity minus 1. So if I see a singlet, how many neighbors must that group of hydrogens have? None. What if I see a doublet? That means there's 1 hydrogen in the neighboring group. If I see a triplet, that means there's 2 hydrogens in the neighboring group. And a quartet, 3 hydrogens in the neighboring group, et cetera, et cetera. Right? So this splitting pattern tells us about what's happening on our neighboring carbon, or rather, how many hydrogens are on our neighboring carbon.
Is that like a combination? Like there might...
Yeah, so you might have 2 on this side and 3 on this side, so that'd be a total of 5 neighbors. All right, so what we're going to do is we're going to take a look at a simple molecule, and we're going to see if we can't predict what's going to happen with our H1 NMR spectrum, similar to what we did before. All right, so first, I guess, let me be clear. What is it that we're going to try to predict here? All right, number of peaks. All right, this 3-carbon propane here, that's what this molecule is. How many peaks would we expect to see in our H1 NMR? How many chemically distinct groups of carbons do we have, or groups of hydrogens do we have? Again, we got that plane of symmetry down the middle. So these 2 are in one group, and this one is in its own group. Okay, so number of peaks. Should get 2. All right, looking at our chemical shift. right, let's try to figure out which one would be further downfield. All right. Remember, downfield is which direction, left or right on my spectrum? Downfield's left, all right? So higher ppm for downfield. So let's look here at our little cheat sheet. One of those is a CH3, the other one a CH2, so which one's further downfield? Downfield higher ppm, so that one in the middle, I colored in green here, should be further downfield. So this is my green. All right, what about the integration of those two peaks, now corresponding to the number of hydrogens that are in that chemically distinct group? How many, what would be the integration of my orange peak? How many hydrogens? 6. And what about my green group? How many hydrogens? 2. Right, so remember we're in an H1 NMR now, so we're talking about hydrogens, not carbons. All right, and lastly, what about my multiplicity? What about my splitting pattern that I would see? All right, so if we look at this orange group here, how many neighboring hydrogens does it have? How many hydrogens are sitting in the group that neighbors this orange group, i.e. this one? 2. So what would my splitting pattern, what would my multiplicity be if I have 2 neighbors? A triplet. All right, and what about my green peak? How many neighboring hydrogens does it have? It's got 3 on this side, 3 on this side. So 6 neighbors, meaning it's going to have a multiplicity of 7, or what we call a septet. All right, and so this is our NMR spectrum for this molecule here, our H1 NMR spectrum. We have 2 distinct peaks. All right. Our green peak here is the one that's further upfield. I can tell because it's got that integration value of 2. To be clear, that's the number sitting at the top here. That's what the computer did. Okay, but most importantly, noting our multiplicity here. As we said, that orange peak should have an integration value of 6, and it should be a triplet. So I have 1, 2, 3 for my multiplicity of that peak. And for my green peak here, it's much smaller because it's got a much smaller integration value. It's only 2 hydrogens in that group. But since there are 6 neighbors, if we zoom in here, we indeed have this 1, 2, 3, 4, 5, 6, 7 septet splitting pattern here, right? Our multiplicity of 7. Okay, so number of peaks tells us how many chemically distinct groups we have. Where on the x-axis we are absorbing tells us about our chemical environment. Our integration value tells us how many hydrogens are in that particular group. And lastly, our multiplicity tells us how many hydrogens are in our neighboring group of carbons, group of hydrogens rather. All right, so these 4 pieces of information we get from an H1 NMR spectrum, and this is how we're going to determine our shape of our molecule. That's a lot of information in there, all right? We're going to sort of do some practice now going from trying to analyze the graph. First, we started by looking at the molecule and trying to predict what our spectrum would look like. Now, what if we're given a spectrum? How can we predict what our molecule is? All right, so first of all, we'll always have these other 2 pieces of information that we've talked about. So we'll do our IR spectrum that will tell us about our functional group that's present, and we'll do our mass spec that'll tell us about our chemical formula. So for right now, I'm going to tell you that we have a molecular formula of C5H10O, and I'll tell you that from our IR, we know there is a carbonyl group. All right, we can go a step further. We know that it's a ketone. All right, so here's our proton NMR, H1 NMR spectrum. And what I'm going to do is I'm going to put down a few ketones, and I want you to tell me which one would correspond with this spectrum below. Because this is actually a lot of information here. If we know our chemical formula, we can sort of put down some examples and try to match them to our NMR. All right, so we got 3 examples here of ketones with 5 carbons, and you're going to figure out which one is consistent with this NMR spectrum below. All right, what we can note is notably what's absent is this integration value here. That's because I really want you to focus on the multiplicity aspect of this, making sure that your structure that you pick is consistent with the multiplicity pattern of these 2 peaks. All right, so let's go through. How many chemically distinct groups do we have here in this molecule? So all 5 of these carbons are distinct. All right, but how many peaks would I expect to see on my H1 NMR spectrum? It's only 4. Why is it only 4? One of them has no hydrogens, right? Let's look carefully here. We got 4 chemically distinct carbons, but one of those carbons, that blue one, doesn't have any hydrogens on there. So that wouldn't appear in my H1 NMR spectrum, different from a carbon-13 NMR spectrum. But for this molecule here, I would expect these 4 peaks. What about this molecule? How many peaks would I expect? How many chemically distinct groups do we have? How many chemically distinct carbons do we have? So we got 3, but again, one of them doesn't have any hydrogens on there, so I would only expect 2. And what about for this one here? So this is a little tricky to see. These 2 are actually going to live in the same group, right? If you shrunk down and you were standing on one, it would look the same as the other. And we'll talk about this a little bit next week, but that's because these single bonds are always rotating about. But that would be distinct from this one here, distinct from this one over here. And then this is a chemically distinct carbon, but again, there's no hydrogen on there. So kind of right off the bat, we can see just this number of signal information will help us rule down which one is it going to be, A, B, or C. It's got to be this one in the middle here. All right, but now I want you to take a second and to assign which one of these peaks corresponds to my green carbons, to my green hydrogens, and which one of these peaks corresponds to my red hydrogens by looking specifically at our multiplicity information here. All right, so importantly, green's only neighbor is red. And how many hydrogens are there in that red group? 2, so we would expect a triplet here. And red's only neighbor is green. And how many carbons are in that green group? Oh, I put that in the wrong place, I'm sorry. Green is our triplet. And then red's only neighbor is green, and how many hydrogens are in the green group? 3. So that's where we're going to get our quartet. And you could also sort of tell this based on their chemical shift. Like we said before, our methyl groups are going to absorb further upfield than our CH2s. All right, but this is how we would assign our peaks here. Okay? And that is the goal that we're going to have. Whenever we look at an NMR spectrum, we're going to immediately go in and label these peaks. Our goal is to propose a molecule, a molecular structure, and to assign those peaks to those carbons in our molecule. All right, so this is what we're going to practice a whole bunch throughout these next few weeks. Let's take a look at another example here. So this is, I'm going to tell you our chemical formula, C3H7Cl. All right, and let me just explain what's going on here. On top, we have our NMR spectrum, our H1 NMR spectrum, and you see the full spectrum. All right, so again, we can go through and label, this is going to be peak A, this is going to be peak B. But then in order to see the multiplicity of each one of these peaks, what I've done is I've zoomed in. So the next box down, that's just a zoomed in image of peak A. And the next box down is a zoomed in image of peak B. So we can count our multiplicity. So here's my full spectrum with peaks A and B. And then I zoomed in to this peak here, peak A. That's what the next one down is. I zoomed in here to peak B. That's what you're seeing here. All right, so given this chemical formula, you're going to tell me what structure of our molecule we have. What molecule do we have here? And so what you want to do first is I'll tell you there are 2 molecules that share this same chemical formula. So draw out those two molecules. How many molecules can you draw me that have that chemical formula, C3H7Cl, and try to match to this spectrum here? All right, so importantly, we got two options, like I said. For my first one, I'm going to put my chlorine on carbon 1. That could be one possible structure that corresponds to that molecular formula. What would a separate molecule be? Chlorine where? In the middle on carbon 2. All right, well, why couldn't I also, I said there were two. What about if I put it on carbon 3? It's the same as which one? The first one, right? Remember, these are 3D structures here. So if I pick it up and flip it like a pancake, it's the same molecule. So this and this are the same thing. All right? These are our only two possible structures here. And so our goal is to figure out which one is consistent with this above. So let me just tell you how we're going to go about analyzing our NMR spectrum. So H1, NMR, analysis table. We're going to, for each peak on our spectrum, we're going to note its chemical shift, where on the x-axis it is. We're going to note its integration and its multiplicity. And we're going to do that for both peaks on that NMR. So I'll make a column for peak A and a column for peak B. All right, so for my peaks here, for the chemical shift, again, I'm talking about where on my x-axis this peak is. If we have a cluster here like this, a peak with multiplicity, we're just going to kind of aim for the middle. All right, so the very middle here will be the ppm that I report, in this case around 4.08, yes. 4.08 for peak 1. Or for peak A rather, And this one, again, kind of aiming in the middle here, we're going to call this 1.22. All right, we'll be good. Label ppm. That's where on our x-axis we're absorbing. What's the integration of peak 1? Where was that integration information? Number of hydrogens, that was that number that's given on top, the area under the curve. So what's the integration of peak A? 1, and what's the integration of peak B? 6. Again, this corresponds to the number of hydrogens that are in each one of those groups. All right, and then lastly, what's my multiplicity of peak A? So we kind of zoomed in here so we could see easier. 1, 2, 3, 4, 5, 6, 7. All right, what we call septet, or you can just leave it as the number. So my multiplicity is 7. And then what about peak B? What's my multiplicity? It's a doublet. I got these 2. 1, 2. So then let's make another one real quick, just for now, number of neighbors. All right, if my multiplicity is 7, how many neighboring hydrogens would I have? 6. And if my multiplicity is 2, how many neighboring hydrogens? Just 1. All right, so then which structure, A or B, corresponds to my NMR spectrum here? It's going to be B. So first of all, we can tell just right off the bat based on the number of peaks that we see, right? For A, I would expect to see 3 groups of hydrogens. And for B, I only see 2 groups of hydrogens, right? So right off the bat, that number of peaks information is already a huge amount of information about your molecule. All right, so we're going to say, all right, it's not this one, but now let's assign our peaks. Which one is A and which one is B? The green one is which one? My septet, right? So it's got these 6 neighbors associated with it. It's got only 1 carbon, so my integration value is 1. All right, it's also bound to that heteroatom, so it should be the furthest down field. So all of this information is pointing to green being A and my orange corresponding to peak B, right? In peak B, I have 6 hydrogens in that group. Its neighbor is just that 1 hydrogen from peak A. And now it's further upfield because it's a methyl group. All right, so that's our goal when we do our NMR. So we're going to create, especially like in the lab, you get this spectrum. You're going to create this table of all that peak information. You're going to propose a chemical structure, and you're going to map those peaks to those atoms in your molecule. That's the name of the game. All right, all that information should point you to a unique structure. Cool. All right, we're going to do one more. All right, so just like before, here are my zoomed out spectrum here corresponding to the molecular formula C4H9Cl. I'm going to label these peaks from left to right, A, B, C, D, and then we zoomed in on peak A here. So this is zoomed in on peak A, zoomed in on peak B, that's what we have next, zoomed in on peak C, zoomed in on peak D. All right, and you're going to try to find a chemical formula that corresponds, or rather a molecule structure that corresponds to our chemical formula and matches our NMR data here. Yes, C4H9Cl. And for the sake of time, I'm going to tell you there are a few different structures that we could draw here. I want you to focus on these two. Try to distinguish which one of these corresponds to our NMR data above. It's either the 1-chlorobutane or 2-chlorobutane. All right, so chlorine on carbon 1 or chlorine on carbon 2. Truthfully, there's some other structures that I could have drawn. This would also correspond. This is also that same chemical formula. But again, for the sake of time, I'm going to go ahead and rule out these two for you. Cool. All right, so here's my H1 NMR data. Which structure is this one consistent with? All right, so for these two structures here, I was able to narrow it down to these two because they both would give me 4 peaks in my NMR spectrum. All right, both of them have 4 groups of chemically distinct hydrogens. So the other ones we could rule out quickly because they would have fewer than 4 peaks, and we could see we got 4 peaks at our spectrum, so we know it's one of these two. All right, so which one do we think it is? The one on the left or the one on the right? It's going to be this one right here. All right, let's convince ourselves of why that is. Okay, so yeah, the doublet was a good giveaway. So if we go through, there's a few things that we want to look at. And this is kind of what makes NMR a pain in the butt, is you don't just like read your spectrum one way. You're constantly going to kind of be bouncing back and forth and making sure that all these pieces of information line up. The first one being the integration. If I looked at my integration on this molecule over here, there's 2 hydrogens in this group, 2 hydrogens in this group, 2 hydrogens in this group, and 3 in this group. If I look at my other molecule, there's 3 in this group, 1, 2, and 3. All right, so looking at my peaks here, I have an integration of 1, 2, 3, and 3. So that's going to correspond to that there. All right, we can also convince ourselves because of the multiplicity here. And in fact, we want to go through and assign which peaks correspond to which. Looking at the integration, we can do so pretty easily. First of all, this one being the furthest downfield is going to correspond to the one with my chlorine on that. And that checks out. Its integration value is 1. So I know this is peak A. I'm just going to go ahead and get rid of this one. It's not this one. All right, what would peak B correspond to? Just looking at that integration value. What color? Yeah, this would be peak B with its integration value of 2. But now we got to look carefully here at C and D because both of these have the same integration value, but they have different multiplicities. All right, so take a second and assign to our molecule here which corresponds to peak C and which one corresponds to peak D. All right, peak C is a doublet, meaning that there's only one hydrogen neighbor. And peak D is a triplet, meaning that there's 2 hydrogen neighbors. All right, so then this one over here is which one, C or D? That one would be C. Its next door neighbor A has only 1 hydrogen. And this one would be D. Its next door neighbor B only has those 2 hydrogens. Cool. So this is how we're going to be analyzing our NMR spectra. For the sake of time, I didn't make that little table, but nonetheless, our goal is to assign our peaks to our corresponding groups of hydrogens in our structure. That's how we can uniquely determine the shape of our molecule. Cool. And we're going to do a bunch of practice with this over the next few weeks.